All right, so now we're going to work up methods to reduce rational numbers. Remember, a rational number is just a number that can be written in the form of an integer over an integer. And remember, these fatty z's just mean integer. It's a shorthand way to say integer or to write it. And why would we ever want to reduce a rational number? Well, let's look. If I had the number, say, 8/6, that's a perfectly good rational number. It has an integer 8 and over an integer 6, totally perfect. But notice that if I divided the numerator by 2, I would get 4, which is totally allowed as long as I also divide the denominator by 2. So if I divide 6 by 2, I get 3. So 4/3 and 8/6 are exactly the same number. They just look different because I have additional factors, or I have not reduced the 8/6 yet. And you can imagine that as algebra gets more and more complicated, we're certainly going to want to work with the most simple form of any number. And so having ways to reduce them makes sense. So let's work up a method for reducing rational numbers. I'm going to use the same number, 8/6, mostly because we've already done it, so we know what the outcome should be, and because it's a simple number to work with in the beginning. So the first thing we want to do in our method is we want to rewrite the number as a product of primes. And remember, POP, right, product of primes for a number, just means using a hockey stick method to factor the numerator and the denominator to write the number out as its prime factors so that I can see what it's made of. All right, so let's go ahead and do that. But remember, when I showed you how to do the product of primes, I told you there was a very specific way to say it while you were doing the hockey stick. Let me show you again. 8 divides by 2, leaving 4, which divides by 2, leaving 2, and 2 is already prime. Right? So that conversation is useful because when you get farther along and you don't want to have to write the factor tree out anymore, you can use the same conversation to write any number as a product of primes in your head, or only writing the prime number. So I'm going to do the same thing up here, but I'm not going to write the factor tree. So 8 divides by 2, leaving 4. 4 divides by 2, leaving 2, and 2 is a prime number. Cool, huh? And so 6 divides by 2, leaving 3, and 3 is a prime. So I'm done. I've written the numerator as a product of primes and the denominator as a product of primes. Now if you look at what we have here, I have a factor of 2 in the numerator and a factor of 2 in the denominator, but 2 over 2 is really just 1, right? That's just 1. So I can cancel those because they're really just multiplying the other factors by 1. And anytime you multiply something by 1, you just get what you get, or what you had to begin with. So 2 times 2, I've canceled everything I can. 2 times 2 is 4, and 3 in the denominator, and that's exactly what we got when we used our logic. All right, let's do another less simple example. Let's take 24 over 36. Now this one's almost easy enough to do in your head. You think of what can I cancel out of, or what could I divide 24 by that I could also divide 36 by, and I'd want to divide as much as I can. And you can almost see, or even see, what the value is, but we're going to do it, we're going to use the method, because that's what we're doing, is learning a method. So 24 divides by 2, leaving 12. 12 divides by 2, leaving 6. 6 divides by 2, leaving 3, and 3 is prime. So without a factor tree, I was able to write 24 as a product of primes. Let's try it with 36. 36 divides by 2, leaving 18. 18 divides by 2, leaving 9. 9 divides by 3, leaving 3, and 3 is prime. All right, so now let's go ahead and do our cancellations, and I just write them as big ones to remind us that the reason you can cancel them is because 2 over 2 equals 1, and there's no need to multiply 1 into a number. It just is the same number you started with. So 2 over 2 is another 1, and then we have a 3 over 3. And I think at this point you probably would have seen divide this by 12 and divide this by 12, and we would have reduced it. And in fact, 2 times 2 times 3 we know is the prime factorization of 12. So I've done exactly the same thing. I've just used an algorithm that'll work on bigger and bigger and bigger numbers. So what did we end up with here? 2/3. And you can see in this case specifically, if I were working with a bunch of fractions in an algebraic process, if I could take 24/36 and turn it into 2/3 because they're equal value, it would be way easier to work with 2/3. So it's valuable to be able to reduce that number. Okay, so let's do one more, and then I'm going to set you free on some examples. Let's look at 56 over, let's do 128. Big challenge here. So let's see what this reduces to. Product of primes, or pop the numerator. 56 divides by 2, leaving 25, 26, 27, 28. So leaving 28. 28 divides by 2, leaving 14. 14 divides by 2, leaving 7. And that's my product of primes. Now, I've done a couple examples without using the hockey stick, and so I just want to hockey stick it to show that I've done exactly the same thing. So 56 divides by 2, leaving, what did I say, 28? So that's that first 2. 28 divides by 2, leaving 14. That's that second 2. 14 divides by 2, leaving 7. That's that third 2, and 7 is prime, so I'm finished. So I did the hockey stick method, but because of the conversation you have with yourself when you're doing hockey stick, you quickly can transition to not having to hockey stick it at all. All right, 128 is big, so let's see. 2, or 128 divides by 2, leaving 64. 64 divides by 2, leaving 32. 32 divides by 2, leaving 16. 16 divides by 2, leaving 8. 8 divides by 2, leaving 4. 4 divides by 2, leaving 2, and 2 is prime. So let's double check this one. I'm going to hockey stick it just to be sure. 128, I'm pretty sure, but I think it's a good thing to show you. So 128 divides by 2, leaving 64. Divides by 2, leaving 32. Divides by 2, leaving 16, divides by 2, leaving 8, divides by 2, leaving 4, divides by 2, leaving 2. I have 1, 2, 3, 4, 5, 6, 7 2s. 1, 2, 3, 4, 5, 6, 7 2s. Phew, that worked. All right, now let's create our 1s, or let's cancel our 1 values. And that's it. So this 56 over 128 reduces to 7 over 2 times 2 is 4, times 2 is 8, times 2 is 16. 7/16. Not a pretty number, granted, but way better than 56 128ths.